Okay, this is part 2, Unit 8A, looking at linear versus exponential growth. And we just looked at a parable of chessboard, and you'll need to review video 1 to get all the details on that, but we're going to pick up here with this first question. So how many grains of wheat should be placed on square 32 of the chessboard? Okay, now remember from the table here, the way you find the number on a single chessboard is you just take 2 to the power of and then 1 less than the square you're on. So if it's number 32, then there will be 2 to the 31 power grains of wheat. And this is massive. 2, 1, 4, 7, 4, 8, 3, 6, 4, 8 grains. And that's how many grains are going to be sitting on piece number 32, or square number 32, and that's, we're over a billion, we're a couple billion there, and we're only halfway through. So you can see this is an exponential growth. Our growth factor is this is what we call 100% growth. Again, if you think about it, you always start with 100%, and then if you grow by 100%, that is 200%. 200% as the decimal is just 2.0. We want to find the total number of grains and their weight in pounds at this point. So again, to find the total number of grains, you just take it, for example here on 5 squares, it would be 2 to the square number and then subtract 1. So this would be 2 to the 32, and then we subtract 1. And this number is massive. 4,294, 967, 295 grains. So that's how many total grains we have after 32 days. And then if we want to figure out how much it weighs, it's 1/7,000th of a pound per grain. So we would take our 4,294, 967, 295 grains, and we would times this by basically when we have our 1/7,000, so this is, we can think of this as 1/7 pounds per grain, and those grains are going to cancel out there. So this turns out to be, when I take that 4 billion and change divided by 7,000, I get 613,567 pounds. And that's how much your total weight would be after putting grain on 32 squares. Okay, and then what's the total weight of all the wheat when the chessboard is full? Okay, so we're going to have 2 to the 64 minus 1 grains. And then again, we're going to multiply that by 1/7,000 pounds per grain. And when I do this out, it's huge. I get 2.64 times 10 to the 15th pounds, and 10 to the 9 is billion, 10 to the 12 is trillion. So we are in the hundreds of trillions of pounds when all is said and done in that little interesting parallel there. So hopefully you can see how much doubling can really add up in a hurry. So we're going to look at this second parable. It's a parable called the magic penny. So one day you meet a leprechaun who promises to give you fantastic wealth, but he hands you only a penny before disappearing. You head home, place the penny under your pillow. The next morning, to your surprise, you find 2 pennies under your pillow. The following morning you find 4, then you find 8, And so apparently the leprechaun gave you this magic penny. Now while you sleep at night, each magic penny turns into 2 magic pennies. So each one doubles itself, basically. So know that on day 0 is the day you met the leprechaun. So if we generalize this table over here, so day 0 you have the amount times the number of pennies. So you have 1 cent. Then you have 2 cents, then you have 4 cents, 8 cents, 16 cents, and so forth. So the general formula is you take the value of the penny, 0.01, times 2 raised to the t power, where t is kind of the number of days later. So there's our general formula here. Now we can use this formula to find out how long it will take until you have a fantastic wealth. So if you look, at t equals 9 days, you have $5.12. Which is barely enough to buy you a lunch or anything small like that. But at the end of the month, at t equals 30 days, you would have 0.01 times 2 to the 30th, which is a pretty healthy sum. You'd be a multimillionaire within a month. And then obviously you'd need a much larger pillow if you have that many pennies under there. And if you keep that going for just 51 days, so 0.01 times 2 to the 51, you'd have $22.5 trillion, which at whatever point in time this was written is about enough money to pay off the national debt for the United States. So the idea of doubling, again, here's another interesting scenario where we can see how fast doubling can help get us increasing. So again, all of this is exponential growth, and our growth factor is 100%. So how much money would you have after 21 days? So remember, you take the value of a penny, times that by 2, raised to the day power, and you'd have, on day 21, you'd have $20,971.52. So after 21 days, you're doing pretty good. Now, let's suppose that you keep making a single stack of the pennies. So every time you get those pennies, you stack them up, and you're able to stack them. How many days will it take the stack to be long enough to reach the nearest star, besides the sun, which is 4.3 light years, or 4 times 10 to the 13 kilometers away? And we assume that 1 penny is approximately 1.5 millimeters thick. So we want to figure out where this is at. So first we need to get this into millimeters. So we take 4.0 times 10 to the 13 kilometers, and we need to convert this into millimeters. So 1 kilometer was 10 to the 6 millimeters. That was from a little while back there. Or it's 1,000,000 millimeters if you want to think of it that way. So this is 4.0 times 10 to the now 19th millimeters is how far away this nearest star is. So next thing we're going to do is we're going to find out how many pennies does this require. So we're going to take that 4.0 times 10 to the 19th, 10 to the 19th millimeters, and remember that 1.5 millimeters was equal to 1 penny. So I would need to take 4.0 times 10 to the 19th and divide it by 1.5, and these numbers are huge. So when you take 4 and divide it by 1.5, you get 8/3, and still times 10 to the 19th, or approximately 8/3 is 2.6 repeated. We'll go 2.67 times 10 to the 19th pennies is how many pennies you would need to get that far away. Now, it says in there, use trial and error. There is a way to get it right down to determine how many pennies you would need, or how many days it would take. As far as total numbers, there's a way to do that, but it involves some math that we haven't introduced in this course. So we're just going to do some guesstimations, and so I would start plugging things into my calculator to find out how many pennies is going to get close here. So as I started doing this, I did 2 to the 50th power. It was too small. 2 to the 60th was still too small. 2 to the 70th pennies, that was actually too big, so I backed it down, and I found that 2 to the 64th power is 1.84 times 10 to the 19th. So that's a little bit small because we need 2.67. So then when I bumped it up to 2 to the 65th power, I got 3.69 times 10 to the 19th. And that's how many pennies I would have on day 65. And so it would be the 65th day is when you would have enough pennies, if you were able to stack them perfectly, to get all the way to this nearest star, which was 4.3 light years away. So again, you can see just how fast this information goes. And if you think about it, day 66, you'd have enough, because it doubles on day 66, it doubles day 65 on day 66. So you would be able to, on that next day, that doubling would bring you all the way back to Earth. It's kind of an interesting concept to think about. So this next one, we're going to be looking at a parable of bacteria. And so I'll introduce it, and then in part 3 we'll finish off the questions. But in our third parable, we return to topic explored that is at the beginning of the chapter. If you want to look at it, it's on page 488. Has to do with bacteria. So suppose that you put a single bacterium in a bottle at 11 a.m. and it grows, and at 11:01 divides into 2 bacteria. Then a minute later, it divides into 4 bacteria. So 11:02, it's into 4 bacteria, which grows, and 11:03 it divides into 8 bacteria, and so on. So now we're going to suppose that the bacteria continues to double every minute, and we are going to, with that background, doubling every minute, I'll start in the next video. I think it'd be most appropriate to end here and start in the next video. But we're going to look at and see that a bottle that is a liter in volume is full after 1 hour at 12 p.m. and just kind of play around with some of the questions here and have a good time with some exponential growth. So we'll continue in part 3.